Everyone, welcome to this talk that will be about reinforcement learning-based dependency resolution. This video was created for DevConf US, that is a virtual event in 2020. I hope you are staying safe. My name is Fridolin, and let's start with a brief introduction about Project Thoth. Project Thoth is a project that is started in a team called AI COE in the office of the CTO, and all the ideas and things I will explain were invented in this project. The project is about making OpenShift a better platform for running AI ML workloads, and as Python is the driving force for AI ML applications, most of the things that I will describe will apply to Python, but the ideas that I will show can be also applied to other programming languages and other ecosystems, considering nuances that differ these ecosystems. Why are we focusing on this? We know that software stacks are complex and they are changing over time, so if you develop an application today, it can get old in 1 year and things change, so it requires maintenance and knowing how the application behaves in the different runtime environments, considering in case of Python, Python libraries, Python interpreter, native packages provided by the operating system, as well as kernel modules and down to hardware, which spans also a lot of variations how you can run your software. We are hosted on GitHub, so feel free to browse our code base, and let's move on to agenda. I will talk slightly about dependency resolution in Python, but this will be really a brief introduction to get the basic idea and principles that are there. And then I will show existing solutions and their pros and cons. And then we will move on and we will describe why we need another solution or why we started inventing a new solution. And that solution will use Monte Carlo Tree Search. So I will slightly discuss about Monte Carlo Tree Search and its variation for resolving high-quality software stacks. And then we will plug this algorithm into resolution pipelines, which make Resolver a configurable piece of software. So let's start with dependency resolution in Python. If you ever used some Python modules, you probably used this site. It's PyPI, the Python Package Index, and it's a repository of software that was written mostly in Python programming language. And as you can see, there are quite a lot of releases, so it's more than 2 million releases of Python modules available out there, free to use, open source, and you can download these Python distributions and use them in your applications. These Python distributions can come also from other indices or other sources. So an example can be TensorFlow. That is a machine learning library that's produced by Google, which is published on PyPI. So I picked a version TensorFlow 2.2.0, and we produced another version of TensorFlow. It's another build that is optimized for AVX instruction sets. So it's more optimized, and you can retrieve it from another source. So PyPI is just one source of these Python distributions, and you can find other sources on the internet and install software from there. If you install some library, most often it depends on some other packages, and this fact is stated using version range specification, and these dependencies can be also conditional. So for example, TensorFlow has nearly 23 packages that are dependencies of TensorFlow, and it has, for example, NumPy, with the given version range specification. Then there is enum 3.4 is a backport to older versions of Python. Of enum module is available in Python standard library starting version 3.4. So there's no point installing it for newer Python interpreters. So that's why this dependency is introduced conditionally if the given Python interpreter version is older. As you can see, these version range specifications do not imply index or index URL, so they really use package name and version range specification that needs to be satisfied in order to satisfy dependency graph or construct dependency graph and satisfy resolve software stack. So let's create some dependency graphs. I've already mentioned TensorFlow in version 2.2.0 that is published on PyPI. And by analyzing it, we observe that it has 23 dependencies. So here you can see them stated all. You see version range specification, some dependencies are optional if environment markers are evaluated as true. And if we try to construct the dependency graph, we really end up with a lot of packages, a lot of software. So here's an example of TensorFlow 2.2.0. Again, it's the one that is installed from pypi.org. And it has some direct dependencies stated as version with version range specifications. And these need to be resolved. So for example, ABSLPy needs to be in version that is above or equal to 0.7.0. And this needs to be resolved, so resolver needs to find what versions satisfy this version range specification. So to this date, there are, I think, 6 versions of ABSLPy that are published on PyPI that satisfy this version range specification. For another dependency, it's more easy because there's just one dependency that satisfies this version equality. For example, NumPy the version range specification for NumPy is satisfied by 21 releases of NumPy, so things are getting worse. And we could continue with all 23 dependencies that are direct dependencies of TensorFlow. These are direct dependencies, and these dependencies can have also, and usually have other dependencies, meaning TensorFlow has some transitive dependencies that need to be installed in order to run TensorFlow stack. So, for example, SciPy will have also some dependencies, NumPy itself will have some dependencies, and we could continue, and we could see quite large dependency graph. This dependency graph can grow over time. So, for example, in the case of ABSLPy, there's stated version 0.7.0, and it could lead to overpinning because if maintainers of ABSLPy that are unaware that TensorFlow uses ABSLPy with some version range specification, release a new software, for example, a new ABSLPy in version 1.0.0, there might be incompatible API changes that will break all the installation of TensorFlow in version 2.2.0 if they resolve ABSLPy to latest version that is released. The same can apply even if there is a new minor release. In that case, this software is again untested with TensorFlow, considering TensorFlow has a good test suite. So again, we can end up with broken software, and there is just a new release, one single library in the whole dependency graph. So if we consider all the direct dependencies of TensorFlow and we compute number of combinations how we can install this software, we can end up with some number, this 3 multiplied by 10 to the power of 13. So this number is quite large and can grow pretty rapidly.
Also consider that we have only direct dependencies. These direct dependencies have transitive dependencies of TensorFlow, so this number grows. And this number is valid only up to this date. So if there are new releases, as in case of ABSLI, this number simply grows. We consider releases that are available only on PyPI in this case. So there are other package indices that are used in the resolution process. Again, this number grows. So these are indices and have patched versions of some libraries with bug fixes and stuff like that. We also consider only direct dependencies of TensorFlow. So if you use TensorFlow together with some another application, for example, another package, for example, Flask, you can imagine that this grows, and dependency graph can be quite extensive and can become quite complex. So if we take a look at the dependency resolution in Python, we already know this dependency resolution is dependent on the environment. The example was enum 3.4. There was an environment marker that stated when the given dependency should be installed into the stack. Things might be even more complicated because these dependencies might be stated in setup py, and the final list of dependencies that should be installed with software can be created dynamically on each installation. That's why we created a tool that is called Thoth solver, and this solver can inspect Python packages and check what dependencies the given library has. This solver runs inside specific environments, so you have a solver that is specific for UBI 8 running Python 3.6, another solver that is specific for Fedora 32 running Python 3.8. In these environments, some packages can have different dependencies, so we really need to inspect how the given package behaves in these environments. In other words, we invest CPU time and we pre-compute dependencies for a later dependency graph construction that we will do later on in this talk. I would recommend an article that was published by Dustin Ingram, and it's called Why PyPI Doesn't Know Your Project Dependencies. That briefly discusses this topic. We created also another article that is called Solving Python Dependencies and How to Beat Python's PIP article series, and it basically describes why PyPI doesn't know Python dependencies, but Thoth's solver knows it. Okay, so let's take a look at existing solutions and their pros and cons when resolving software stacks. I took a listing of resolvers from packaging.python.org, and you are probably familiar with pip, that is the recommended tool for installing Python packages. Then there's pipenv that also manages a virtual environment, manages a log file that is kept in sync with Python packages and Python module that you installed. Then there is piptools, which creates some locking mechanism on top of requirements in and requirements.txt. That is again another format for describing dependencies. There's also community effort similar to pipenv that is called Poetry. And Poetry tries to manage also virtual environment, but also the life cycle of a module that is released on PyPI or other Python package index. pipenv does not have this assumption that modules that are managed by pipenv will be released to some Python package index. There's also micropipenv. This tool was developed within Project Thoth, and it does not actually implement any resolver, but is complementing all the tools that are already stated, and it provides a lightweight tool that can be used to install dependencies that are managed by pip tools, pipenv, Poetry, or raw requirements.txt files.
we use this tool for installing dependencies in containerized environments such as S2I, such as OpenShift S2I. Okay, so why do we need another solution? Why do we need another resolver that needs to be implemented? Or why? What's the story behind it? So all these tools that implement resolver try to install latest software. And what if the latest software is not the great software? What if that software is not the software that I would like to use? If you recall that back with hypothetically released ABSL-PI in version 1.0.0 that broke our software stack, these things happen. And it's quite issue because it breaks the application, and 1 or 2 years later you can end up with a software that you cannot run because you don't know what dependencies should be installed in order to run your software. So let's create a tool that installs packages that are installable into your environment. That's first assumption. So there are no PI issues, maintainers provided correct packaging, so the Python distributions are installable into your environment. Then we want to install software that runs in the given environment. So if we are running Python 3, we don't want libraries that are not Python 3 compliant, for example. Or if there are some breaking changes in Python across releases, we want to run software that respects these changes. Then we want to install software that correctly runs, so there are no bugs on application level. We want to install software that performs well. So if we are running TensorFlow computations, and we have AVX2 instruction set available on our CPU, we want to install TensorFlow that is optimized for our CPU with AVX2 instruction set. That's one example. And at the same time, we want to install software that is not prone to known vulnerabilities. CVEs at one CVE example, but if I'm running some production components, I would like to be sure that its security it's not vulnerable and it's secure to run it. Okay, so let's move on and let's define a way how to find high quality software stacks, and we will discuss Monte Carlo Tree Search algorithm. Before we go deeper into that algorithm, I would like to say why we use this algorithm. So it was not a decision like from one day to another that we will use this algorithm, but we experimented with different approaches that ended up with different results. So we had quite extensive journey to come up to go with Monte Carlo Tree Search, and the very first effort that we made was performing computations directly on the dependency graph. This idea is described more in the linked talk. Basically, we load the whole dependency graph and we tried to adjust it in a way that the resolution process finds the best candidate that is scored respecting packages in the result software stack. So come up with the high quality software. However, this approach was not good because it required a lot of queries to database, and basically the program kept querying the database. Then we tried to optimize it using neural combinatorial optimization with reinforcement learning, where we used neural network. But again, that solution was not scalable and not nice. It did not resolve anything real world. Then we came up with adaptive simulated annealing that was successful. The resolution was lazy, so the queries to database were really the queries that were required when the state space during simulated annealing was sampled. This approach is documented or described in linked talk, and then we came up with an idea of using reinforcement learning. So there were implemented two main approaches. The first one was temporal difference learning,
and finally we compared it to Monte Carlo Tree Search, and Monte Carlo Tree Search was the algorithm or is the algorithm that we use as of now for resolving software stacks. Why? I will tell it. I will say it in a few minutes. So, what is Monte Carlo Tree Search? If you browse Wikipedia, it will say something like, in computer science, Monte Carlo Tree Search is a heuristic search algorithm for some kinds of decision processes, most notably those employed in software that plays board games. In that context, Monte Carlo Tree Search is used to solve the game tree. Okay, so we are playing some games, but not really in the resolution process. There is no real opponent when we want to resolve software stacks. So at first the idea looked shady, but with some adjustments to Monte Carlo Tree Search algorithm, we were able to apply principles that are in Monte Carlo Tree Search, and we created a variation of Monte Carlo Tree Search which uses adaptive simulated annealing for balancing exploration and exploitation. So I will talk about this in a minute as well. The real opponent that we created is imaginary component, because we are not really playing any board games, and this imaginary opponent is CPU time, or time needed to satisfy user requests. So we wanted to have our recommendation engine as responsive as possible. So if a user comes to us and asks what software should he or she use when running TensorFlow, we wanted to give recommendations in a reasonable time, and that's the opponent we are playing against. We know already that the state space of all the possibilities, all the packages that are possible or available in the dependency graph, that state space is too large. So we really need some heuristics how to browse the dependency graph and how to behave in the dependency graph. If you are familiar with Monte Carlo Tree Search or model-free reinforcement learning methods, you probably know Markov decision process. I will talk about this process, but basically we whole resolution process is an MDP that needs to be solved. MDP meaning Markov decision process. We are looking for software that has high quality. So we want to solve MDP by accumulating high reward, and software stacks with highest possible cumulative reward are the software stacks that we are looking for, the software stacks that have high quality. We will dive into this idea as well. It's worth to note here that Monte Carlo Tree Search is one type of predictor in our component, in our recommendation engine that is called advisor. And the predictor is abstraction that we've created in the implementation. So there are also other abstractions. So you see predictor, that is the implementation of Monte Carlo Tree Search, adjusted using adaptive simulated annealing principles. And then we have other predictors for resolving latest software stacks, or another predictor that uses temporal difference learning, or another predictor that uses adaptive simulated annealing. And there are also other predictors that we've experimented with. For example, a predictor that tries to resolve always one package to compute all the combinations in the stack. So, for example, if you want to test TensorFlow with different versions of NumPy, we can pack a predictor that can narrow the resolution process to desired set of software stacks much faster. So this is the idea of predictor abstraction, and in the slides you will also see other abstractions such as resolver that abstracts away the resolution process that is combined with Python standards. So the resolution process resolves software stacks that respect version specifications and also environment markers in the resolution whole resolution process. And then predictor acts as a as a guide who helps predictor to resolve software stacks. There is also another abstraction that is scoring pipeline, and I will talk about it later on. So, Markov decision process. Again, we will check a few sentences from Wikipedia, and then we will dive into examples to understand the idea and adjustments we've made more deeper. So in mathematics, a Markov decision process is a discrete time stochastic control process. It provides a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision maker. MDPs are useful for studying optimization problems solved via dynamic programming and reinforcement learning. So this is the definition that was obtained from Wikipedia, but we will take a look at MDP that was kind of adjusted to our needs and adjusted so that it could be used in a resolution process. So a resolver that is implemented in Thoth is using a list or set of states. This abstraction is called beam, so it's a beam of states. And these states are partially resolved, so they do not state all the dependencies that form a final stack, but they keep just few resolved packages or non-resolved packages, and packages that are about to be resolved. So each state has two sets. One corresponds to packages that are resolved, and another set that has that holds unresolved dependencies. If a state holds no unresolved dependencies, it means it's a final state, and all dependencies that are present in the resolved set form the final stack that is resolved. If a resolved set has no dependencies, that means that we have an initial state from where we start by expanding unresolved dependencies, in which case unresolved dependencies are direct dependencies of our application. So the whole process, Markov decision process, is basically solving or resolving the dependency graph. This resolution respects Python dependency specification as stated before, and there are actions that are done. So I've already mentioned that we have resolved set and unresolved set of dependencies, and if we move a dependency from unresolved set to resolved set, then this is called an action. In MDP, in resolver's implementation, it's called resolver steps. By doing so, by moving unresolved dependency to the resolved dependency set, we obtain some reward signal that can be positive or negative, meaning if including a given package in the stack is something we want to do, like positive, then we have positive signal, and if it has some drawbacks, such as the given package has vulnerabilities, including it in the software stack can have a negative impact, and in that case the signal is negative. After the resolution process is done, we backpropagate information about rewards computed, so information about accumulated rewards. That is case of Monte Carlo Tree Search. In case of TD learning, the backpropagation is done immediately after the step is done. So that's the only difference between Monte Carlo Tree Search and TD learning when it comes to implementation. Okay, so maybe let's have a look at some details. So let's consider that we have some state as n, and this state is formed out of resolved dependencies set and unresolved dependencies set, as stated before. In resolved dependency set, we have Flask in a specific version that is installed
from pypi.org, and in the unresolved dependencies set, we have dependencies that can be included into our software stack in specific versions. So I have options, like if I want to use, if I want to include click in my software stack, then I have two options. One is install click in version 6.7 or install click 7.0 from pypi.org. Which one? That's up to predictor, which will tell resolver which version should use. So we have this state as n, resolved dependencies, unresolved dependencies, and we have also score that corresponds to this state. And what we want to do, we want to, in this case, we are programmers, we want to maximize this score. If we would be mathematicians, we would probably minimize that score, but we want to maximize it. So this state Sn corresponds to this node in the graph, and here are encoded options that we can take. So we have this state Sn, and what we do, we ask predictor which dependency should resolver, meaning I, which dependency should I choose to resolve the software stack. And predictor, it can be MCDS, Monte Carlo Tree Search, DD learning, or it can be adaptive simulator annealing, any other predictor, says that we want to resolve, we should resolve Jinja in version 2.10.2 from pypi.org. So let's do it. If we do it, then we need to adjust the state in a way that we don't consider Jinja 2 as unresolved dependency and move it to resolved dependencies set. This move or this action that was taken says that we have immediate reward signal that is 0.2. So we adjust our score in newly created state so that it at 0.2 as a reward signal that we obtained. Then what we need to also do, as we moved Jinja to resolve dependencies, we need to resolve dependencies of Jinja. So we need to ask resolver what Jinja 2, what are dependencies of Jinja 2. So in this case, it says markup safe inversion above 0.23 and bubble above 0.8 that need to be resolved in specific versions that are known and are available. I skipped this part. The reward signal that we obtain can be also none or infinite. This is just implementation detail. So if the given transition would not be valid, we would obtain a reward signal that is a number. And if the resolution process would lead to a final state, then the final or the reward signal would be infinite. That would be propagated to predictor, so predictor knows that expanding this dependency leads to a final state. Okay, so we know that we need add unresolved dependencies from resolving Jinja 2 in that specific version, and it again adds new packages to unresolved dependencies in state Sn+4, and we continue this process until we don't have any packages in the unresolved dependency set, and in that case we would have the final state, which states fully resolved software stack with some score that corresponds to cumulative reward signal. So this was one performed one action during the Monte Carlo Tree Search resolution, and in case of Monte Carlo Tree Search, we continue this process until we reach one leaf node, and then we backpropagate information about score to parent nodes, meaning the nodes that were created out of the original score. So in case of state Sn+4 that we computed, we propagate information about score to parent nodes, so the predictor can learn how
how the resolution process looks like and how these packages or how these software stacks are scored in the whole state space. I already said that we had to adjust Monte Carlo Tree Search, and that adjustment lies in balancing exploration and exploitation. These are two terms. If we want to observe the state space, like how it behaves when we resolve certain packages, then we do exploration. We learn how software stacks should be resolved in order to come up with a set of packages that form the final stack with very high final score. Then what we do exploitation. So a predictor learns how to resolve software stacks, and then during the resolution process, this predictor knows which packages should be resolved in order to maximize the reward signal. It's quite good to state here that in opposite to board games, we most of the time don't end up with same state, same node during the gameplay or resolution. So what we do, we average how the state space behaves when we add certain package. So on average, for example, if we add Jinja 2 to our stack in the version that we saw, on average we obtain a reward of 0.2. Then we state the fact in the predictor's predictor's history. Okay. So to balance exploration and exploitation, we use adaptive simulating annealing principles, in which case we have temperature that is set to some high number, and over time it decreases. And factors that form this adaptive simulated annealing are number of stacks that are resolved, or number of iterations, number of rounds done in the resolver, number of actions taken, and so on. So we really limit time spent in the resolution to come up with recommendations. We also designed a random number generator that's called terminal random that helps us to narrow the resolution more closely to latest software, but not use latest all the time. So this was the idea about resolving software stacks in really large state space. And as you've already seen, there are too many possibilities to be checked, and a number of combinations grow really significantly with each package added to the software stack. So we already know that there is no way how to check all the possibilities in any real-world applications. So we created these heuristics to find the high-quality software stack as soon as possible. We found that reinforcement learning is the way to go to resolve high-quality software stacks. The last thing that I would like to discuss is resolution pipeline. So you already know that we are taking some actions in MDP, and these actions correspond to steps. So we created an abstraction that's called resolution pipeline, and this pipeline is created out of units. These units have their separate semantics. So there is a unit that scores packages based on performance, based on security and stuff like that. The idea is that latest software is not the greatest one, so let's plug pipeline units that have some knowledge about software and can guide a predictor in resolution by scoring and sending the reward signal during the resolution. So we have different pipeline units based on their semantics. They do one thing and they do it properly, so they follow Unix philosophy, and they form some kind of programmable interface to the resolution process. As we will see, these pipeline units are very straightforward to implement. The user of this recommendation engine, or the programmer of this scoring pipeline does not need to know about all these MDPs and stuff like that, so it's abstracted away. It's important to also state that these pipeline units are plugged into the resolution process dynamically. That means they are asked to be included. I will show you in a minute how it works. So the resolver accepts a vector of information. So for example, direct dependency, software environment, and hardware that is used, libraries that are used together, some static source code analysis, like what API calls are performed, also recommendation type. So if a user wants to use secure or performant software, so these are input vectors into the resolution pipeline that is created out of units. And then together with a resolver and predictor, there are created pinned down software stacks considering knowledge that we have about these packages. So let's have a look at an example of a pipeline unit. This pipeline unit is called a step and scores TensorFlow builds that are optimized for AVX2 enabled CPU processors if user uses AVX2 enabled processor. So there are two important methods. One is called run and the other one is called should include, that is class method. And there is also AVX2 CPUs. So let's take a look at the implementation. The listing of CPUs is quite straightforward. It holds a couple of two integers that describe CPU family and CPU model of Intel processors that support AVX2. So these are basically constants. Then there is that should include class method that asks this step whether it should be included in the resolution process. So it checks what recommendation type user requested, and if the recommendation type should be performance or the user wants stable software, we include the pipeline unit. We also include it if and only if the user uses CPU that is capable of AVX2 instruction set. So that's the only case when this pipeline unit is included. The semantics behind this class method is that if it returns none, the pipeline unit is not included, and if it returns a dictionary, then it is included. The dictionary has special meaning. I don't want to go into details, but there is a reason behind returning a dictionary. Then there is another method that is called run, and this corresponds to the action that is performed in the MDP. So we are in some state and we want to go into another state, and that's another state is created by including package version into the current state. So the run method accepts two parameters that are state and package version to be included into the state. If the package version to be included is TensorFlow and it supports AV and the included TensorFlow supports AVX2 instruction set, then we propagate a reward signal that is positive, and we also say some informative message to user. So we are coming to the end. This was a brief introduction to the resolution process that is using reinforcement learning. This all was done in Project Thoth, so if you are interested, feel free to reach out to us at Thoth Station Ninja. We are part of AICOE, Office of the CTO, so you can also find us on Google Chat. The source code is hosted on GitHub, the Thoth Station organization. We have also a Twitter account with Thoth Station handle, and that handle has some dash in it, so be careful who you follow. And we have also a YouTube channel where we periodically send or publish videos from our Scrum sessions and also some interesting talks that we found. If you follow us, you will find more information about distributed environments, about, for example, Argo workflows, Tekton pipelines, RCD, all this cool stuff, like also performance of machine learning libraries and stuff like that. So it's not just about this reinforcement learning algorithm, but also other things that might be interesting to you. This way, I would like to thank you for your attention and hopefully see you next time. Thank you.